Hello everyone, let's analyze. Alright, so now we know what it means for a sequence to converge to a limit, and we also know what it means for a function to converge to a limit. Now, exactly how are these ideas connected? Can a function be determined to converge by evaluating sequences? Well, the following theorem ties the ideas together. Let x naught be an accumulation point of D, which is a subset of R, then the following statements are equivalent. The function f has a limit at x naught, that's statement 1. And statement 2 is, if xn is a sequence of elements of D, none equal to x naught, but convergent to x naught, then the sequence f of xn converges. Well, let's prove the statement. Now, before we get into the nuts and bolts of the proof, let's huddle up and talk strategy. When we say that two statements are equivalent, what we mean is that if one of the statements is true, both are true. And if one of them is false, the other must be false. So in fact, one perspective is to say that statement 1 is true if and only if statement 2 is true. And that is a valid perspective. And of course, we can prove the theorem by showing statement 1 implies statement 2, and statement 2 implies statement 1. But another way to prove the statement is from the first perspective, which is to say that if one of the statements is true, both are true. If one of the statements is false, both are false. Specifically, we're going to show that if statement 1 is true, statement 2 must be true. And then we're going to show that if statement 1 is false, statement 2 must be false. Now, in fact, this is logically equivalent to proving that statement 1 implies statement 2 and statement 2 implies statement 1. Why is that? Well, step 2 is in fact the contrapositive of statement 2 implies statement 1. Remember, the contrapositive is A implies B, is not B implies not A. In fact, just so that we're on the same page, let's quickly discuss what we mean by contrapositive. A note on the contrapositive. Now, while proof by contrapositive may sound like some advanced sorcery, it's really just a term to apply a common sense idea that we likely apply daily. Imagine that it was an inviolable law of the universe that every time I arrive to the party, the song Return by R&B superstar Mark Morrison played. In other words, my arrival implies hits the boombox. Then if someone asks you whether the professor came by, but you realize hasn't played, then you can conclude that the professor is not in the house. No implies no arrival. Now, while this may register only as common sense to most, it is in fact an application of the law of the contrapositive. Okay, back to our theorem. Okay, so remember, our strategy shows statement 1 implies statement 2. Statement 1 and false implies statement 2 must be false. So, suppose f has a limit at x naught. Let's call it L, since we're so creative. Then, for any positive epsilon, there is a real delta for which the following is true. If x is in the domain, and x is within delta of x naught, then f of x is within epsilon of L. Right? So this is true because we're supposing f has a limit at x naught, right? So by supposing this, right, this is all that we can take to be true, which is, of course, the definition of a function having a limit. Now we got to show that step 2 is true. Well, if xn converges to x naught, we need to show that f of xn converges as well. So, if xn converges to x naught and satisfies the condition that each element is in the domain but none equal to x naught, we know there is a natural number n such that xn minus x naught in absolute value is less than, well, whatever real number we want, and we choose delta. Of course, it's greater than 0 in absolute value because xn is by definition not equal to x naught. And this statement is true for every n greater than that natural number big N that exists. Then, the fact that my function has a limit, the fact that this is true, implies that for n greater than or equal to this natural number n, since this is true, I'm guaranteed that this is true for xn. And that proves my result. My result that the sequence f of xn converges. And we also showed specifically it converges to L. Right, by the way, if I take the statements in red together, that's exactly the definition of a sequence converging to a limit. For any epsilon greater than 0, there exists a natural number n. If n is greater than big N, then f of xn minus L in absolute value is less than epsilon. I've demonstrated that the sequence f of xn satisfies the definition of convergence. Now, I actually demonstrated something a little further, that every sequence f of xn that converges must converge to L. So, we've shown that step 1 is true. Statement 1 implies statement 2. Now step 2. But before we get deep into step 2, a quick note. If I look at the theorem statement, a convergent sequence xn to x naught implies that f of xn converges. The statement does not say that it implies that f of xn converges always to the same limit. But in fact, it's implied in there if not explicitly stated. Well, how is that? If any sequence xn converges to x naught implies that the sequence f of xn converges, then it must converge to the same limit L. Well, because if xn converges to x naught and yn is a different sequence, also converging to x naught, then I can interlace those sequences and I would have a new sequence that also converges to x naught. And remember, a sequence converging to x naught implies that f evaluated at that sequence also converges. Now, notice that I know that the odd and even subsequences of this sequence both converge. And I also know that the entire sequence converges. And if the entire sequence converges, both subsequences must converge to the same limit. Therefore, f applied to the sequence xn and to the sequence yn must have the same limit. Okay, now that we got that out the way, let's suppose statement 1 is false. Right? In other words, f has no limit at x naught. For all possible limits L, there is an epsilon greater than 0, and for every delta greater than 0, there's an x in the domain that satisfies both this statement, x is within delta of x naught. However, f of x is at least epsilon away from L. Now, let's make very clear what our goal is. We want to show that by assuming statement 1 is false, we must show that statement 2 is false. Okay? In other words, to show statement 2 is false is to say that the negation of statement 2 is true. And the negation of statement 2 is that there is a sequence converging to x naught. However, f of xn does not converge to any number L. Now, since delta is arbitrary in the statement 3, and remember 3 is true, right, by supposition of the fact that statement 1 is false. So since delta is arbitrary, for every natural number n, there's an element of D, and let's call it xn, satisfying this condition for x equals xn, but also satisfying this condition. Now, since 1 over n can be made arbitrarily small, the sequence xn converges to x naught. However, since f of xn is bounded away from L for any arbitrary L, then f of xn minus L can never be made less than epsilon in absolute value for every value of n, for any value of n. So the sequence f of xn does not converge to any number L, and the theorem is proved because we have shown that statement 1 implies statement 2, and statement 1 being false implies statement 2 as being false, which means the two statements are equivalent. When one is true, they're both true, and when one is false, they're both false. Now, let us all behold the power of this theorem in action. So, that beautiful plot right there at the top of your screen is sine of 1 over x, a beautiful function. It basically takes sine of x and takes the line from 1 to infinity and compresses it and reverses it into the interval 0 to 1. That's beautiful. Does it converge though? Does the function f of x equal sine of 1 over x, does it converge at 0? Well, right? In other words, we want to know, is statement 1 of our theorem true or false? If we want to show it's false, we can do it by showing that statement 2 of our theorem is false. In other words, if we can construct a sequence converging to 0, however f of xn does not converge, then we have shown that sine of 1 over x has no limit at x not equals 0. Well, first, let's consider the sequence sine of n pi over 2, right? So in other words, sine of half a pi, which is 1, sine of pi, which is 0, sine of 3 halves of pi, which is negative 1, sine of 2 pi, which is 0, sine of 5 pi over 2, which is 1, so forth and so on. Remember that sine is the y-coordinate of the unit circle, right, parameterized by angle. So if we're counting by half of pi's, we're basically hitting the positive x coordinate, the positive y, negative x, bottom y of the circle. Of course, we can see that since the sequence is 1, 0, negative 1, 0, 1, and it repeats in that pattern, it will not converge. It'll never settle or get arbitrarily close to any one number. Now let xn be the sequence that satisfies 1 over x, right, the argument of our function, 1 over xn equals this argument here, n pi over 2. Well, if xn equals n pi over 2, then xn is equal to 2 over n pi. Now, it's clear that if I take 2 pi and divide by n for n equals 1, 2, 3, 4, and so on, that xn converges to 0, but is never equal to 0. Therefore, sine of 1 over xn does not converge, but xn does converge. Therefore, statement 2 in our theorem is false. In other words, xn converging does not imply f of xn converges. And since statement 2 is false, statement 1 is false, meaning that the limit of sine of 1 over x does not exist at x not equals 0. Now let's stop and look a little bit at this plot of sine of 1 over x. By the way, the red dots, that's sine of 1 over xn. We can see that x1, x2, x3, x4, x5. And of course, I'm running out of space, but here's x6, x7, x8. Of course, the sequence x converges to 0. But if I evaluate sine at these points, I get 1, 0, negative 1, 0, 1, 0, negative 1. And of course, the pattern repeats. What a beautiful function. Well, that's it for today.